Jupiter is far more mysterious than most people realize. Many of the common beliefs about this giant planet are actually incorrect. It isn't just a massive ball of gas, as often taught. It's primarily a liquid planet, and beneath its swirling clouds lies something even stranger, a deep ocean of liquid metal. This hidden layer is one of the most fascinating mysteries in our solar system. Let's explore what lies beneath those iconic bands of color. The first close-up image of Jupiter was taken by NASA's Pioneer 11 spacecraft back in 1974. Then, in 1979, Voyager 1 captured the first moving footage as it approached the planet. While these images were stunning, they didn't reveal Jupiter's true composition. They only deepened the mystery. What exactly is this giant made of, and how did it grow so immense? Jupiter's size is almost beyond comprehension. It's not just large, it's heavier than all the other planets in our solar system combined. You could fit about 1,000 Earths inside Jupiter. To put it in perspective, if Earth were the size of a grape, Jupiter would be as big as a basketball. Most theories about the formation of our solar system begin with a vast disk of rock, metal, gas, and dust swirling around the young sun. Over millions of years, these materials collided and merged into larger bodies. As these bodies grew, their gravity attracted even more material. According to this idea, Jupiter formed when one of these growing chunks became massive enough to pull in huge amounts of gas from the surrounding disk, eventually becoming the giant planet we see today. If that were true, Jupiter would have a solid, dense core of rock and metal at its center. Another theory suggests Jupiter began as an enormous cloud of gas located just outside the early solar system. Over time, this cloud collapsed under its own gravity, forming a dense ball of gas, similar to how stars form but on a smaller scale. Eventually, the sun's gravity captured this new planet, pulling it into orbit. In this scenario, Jupiter might not have a solid core at all, instead resembling a layered structure of gas. The idea of a solid core capturing gas seems logical, but it turns out that's not quite accurate. Our understanding of Jupiter took a major leap forward in the mid-1990s, thanks to an incredible cosmic event. In July 1995, a comet named Shoemaker-Levy 9 collided with Jupiter. Such impacts are rare, estimated to occur only once every 6,000 years, but we were fortunate enough to witness this one. The comet, traveling at 216,000 kilometers per hour, had already been broken into dozens of pieces by Jupiter's intense gravity. The largest fragment was about 2 kilometers across. NASA's Hubble Space Telescope was ready to observe, but there was a challenge. The impacts were happening on the far side of Jupiter, out of Earth's view. Amazingly, at that very moment, NASA's Galileo spacecraft was approaching Jupiter. Launched in 1989, Galileo was on a mission to study Jupiter and its moons, and arrived just in time to witness the comet strike. Over 6 days, it recorded 21 separate impacts, the largest released energy equivalent to 300 million atomic bombs, the largest explosion ever filmed. As Jupiter rotated, Hubble captured the aftermath. Dark scars in the clouds and towering plumes of debris that lingered for months. Galileo flew through this ejected material, giving us our first glimpse beneath Jupiter's cloud cover. One of the most surprising discoveries was the presence of water, a lot of it. This finding prompted scientists to design a new mission specifically to uncover Jupiter's secrets. That mission, named Juno, launched in 2011 and arrived in 2016 to investigate the planet's core. So, what have we learned in the past decade that changes everything? Jupiter isn't made of gas. It's enveloped by thick clouds of gas that create its famous storms and bands. But these clouds are just a thin layer atop much stranger phenomena below. Starting from the top, the cloud temperatures on Jupiter dip below -100 degrees Celsius. Water ice crystals mix with ammonia, which acts as an antifreeze, allowing liquid water to exist in the upper atmosphere. When droplets collide with ice, the clouds become electrified, triggering massive lightning storms. This mixture forms slushy hailstones that fall into the lower atmosphere, melt into rain, evaporate, and rise to begin the cycle again. Jets of hot gas rise from deep within to fuel storms like the Great Red Spot. This enormous storm is thousands of kilometers wide and extends hundreds of kilometers down into the atmosphere. It towers higher than any other cloud on Jupiter, absorbing more ultraviolet light from the sun. This interaction with chemicals gives the spot its deep red color. Imagine a cloud 10 times taller than Mount Everest and 10 times deeper than the ocean. That still wouldn't match the scale of the Great Red Spot. As spectacular as these outer layers are, the clouds of ammonia and water only extend about 50 kilometers deep. Below them, temperatures rise due to increasing pressure. Gravity compresses molecules, concentrating their energy. The deeper you go into Jupiter's gravity well, the more heat and pressure build up. It's like moving through a fog that grows denser until it turns into liquid. But here, the fog is hydrogen. Hydrogen, the lightest element, is the only one that can remain buoyant in such intense gravity. Heavier elements sink toward the core. About 1,000 kilometers below the cloud tops, hydrogen gas becomes a liquid, forming an ocean of liquid hydrogen, the largest ocean in the solar system. So, while Jupiter is covered by a thin layer of gas, it's fundamentally a liquid planet. But this isn't like any liquid we know. On Earth, hydrogen becomes liquid at extremely low temperatures. On Jupiter, intense pressure raises its boiling point so high that it remains liquid even at temperatures exceeding 1,000 degrees Celsius. This ocean is about 20,000 kilometers deep, 2,000 times deeper than Earth's oceans. At the bottom, under millions of times Earth's surface pressure and temperatures around 10,000 degrees Celsius, hydrogen undergoes another transformation. It becomes metallic hydrogen. This doesn't mean it turns solid like metal. It remains liquid but with metallic properties, similar to mercury in a thermometer. In this state, hydrogen can conduct electricity. Jupiter's gravity is so powerful here that electrons break free from hydrogen atoms, flowing freely and generating electric currents. This layer of liquid metallic hydrogen makes up most of Jupiter's interior, extending about 40,000 kilometers deep. At the very center lies Jupiter's core, but it's not what we once thought. Scientists previously believed in a compact, Earth-sized core made of iron and rock. New research, however, suggests the core is fuzzy, with no sharp boundary between the liquid metal and solid material. Instead, it's like a dense, mixed soup of liquid, rock, and metal, spanning about half the planet's radius. It's unclear whether this is unique to Jupiter or common among gas giants. Saturn hasn't been studied as thoroughly, so we can't be sure. If Jupiter's core is unusual, it might be the result of a colossal collision early in the solar system's history, perhaps with a rocky planet 10 times Earth's size. The impact could have scattered and diluted the solid core. This might also explain how Jupiter grew so large. While the collision theory is compelling, recent computer simulations show that such impacts would create a fuzzy core, but it would relatively quickly re-solidify into a distinct central ball. So, we know Jupiter has a strange, blended core, but we still don't know how it formed. Despite all we've learned, the origin of this giant planet remains one of astronomy's great puzzles. Jupiter is a captivating mystery, waiting for us to uncover its secrets. If you enjoyed this journey into the heart of Jupiter, make sure to subscribe, like, and share this video with fellow space enthusiasts. Your support helps bring more cosmic wonders to light.